here with the date for when we cover that topic. So if you miss a day of class, you can not only see Daniel's video, but you can also come here and see what was written up and filled in. You can also go here. I've posted some old tests and reviews for old tests from previous, from fall 2012. I don't know why I picked that semester. It just seemed to, have a good bunch of stuff that I could go ahead and upload. So when you go to the end of Test 3's notes, the very last link is a review for Test 3. And it refers to not only the topics that are on Test 3, but it says, go back here to Crossland's old test and reviews and work these problems from Test 3, Fall 2012, these from Test 4, Fall 2012, and these other problems. Those tests, along with their answer keys, are there, so you can double check your work and make sure everything's okay. What I've uploaded from the other night, if you notice a handful of folks who have those blank lecture notes with them, I'm going to always put those here, regardless of what test. I'm just going to make one big series of links that go from what we started with until the end of the semester. Hopefully over the weekend, I'll get everything uploaded that we'll need from now until, end of April for the complete set Test 3 and Test 4. And occasionally you'll see some homework exercises that are supplemental. You have the option of skipping the textbook homework and just doing the problems that I've posted up here, because that'll just be, like I said the other night, those are problems that I've written up that I like from a textbook that I really enjoy using. We don't adopt that textbook for some reason, but anyway, that's just some problems that I've put up there. And the solutions will be put up there as well. So like the D-test problems that you started from Tuesday night, those solutions are up there. And I paired them right after each other. Here's the notes for the blank notes for D-test and the supplement problems, and here's the solutions. Here's the notes for double integrals. Here's the supplement and the solutions. So it's kind of in order of how everything's done. So if y'all have any questions on this, I don't mean to intimidate you with the use of D2L, but I use it pretty extensively. So that's one major change that you probably noticed. So hopefully it's not throwing too big of a kink in your cog work. Okay. Do you have any questions for me? Homework or not meaning of life? I'm sorry. Negative as well. So did you get a chance to try some of the D-test problems, or even gradient, directional derivative, chain rule stuff? No. So at least you're honest. So your study habit is to sort of wait closer to test time and then picking all of that.
I have matrix.
Yeah. So. Sorry, Chris. I'll agree with you. I've never taught it and never intend to. It's just too dry. Well, barring any questions, we'll go ahead and kick off with double integration. However, let's hop in our TARDIS and hop back in time for a little bit. Pardon?
I love Doctor Who.
Yeah. I didn't watch it for the longest time,
Yeah.
but I kept. By the time I had the 45th student come up and say, "You need to watch Doctor Who," I was, okay, apparently I need to watch this. So I binge watched it on Netflix a couple of years ago, and I liked it. So, and Tenet's my favorite one so far. So, so hopping in our TARDIS, going back in time from Calculus 2, early Calculus 2. When you first saw this, or when you first were, discussing this or introduced to this, do you remember what the context was? In other words, what was the first purpose that you were taught this measures? Area under a curve. Yeah. In most every Calculus 2 class, the defining premise for the definite integral, it comes from Riemann sums and taking the limit for that Riemann sum, for finding the area under a function's graph between the x-axis and the graph of some oddly shaped regions like this. If your function f of x, it's got some nice continuity to it, no asymptotes, no kinks, nothing that's going to make an improper integral. This was first introduced to you as the two-dimensional area above the x-axis below the function of that region. Okay. And then, integration went into some other applications and other meanings. Eventually you learned how to deal with volumes using revolution solids and centroids. And some of you probably covered the work problems involving physics and a variable force and stuff like that. So there's a lot of things you can do with this. We're going one dimension higher. But, it's a pretty much of a natural extension. The way this was developed is you break this interval down into, little tiny delta x subintervals of equal length. They don't have to be of equal length, but just for convenience, it's usually easiest to do that. And then using either left endpoints or right endpoints at each of those intervals, you develop these little Riemann sum rectangles that approximate the area, and in the evaluation of a limit, each of these rectangles gets skinnier and skinnier as delta x shrinks down infinitesimally small to a point. And when that happens, the delta x becomes the differential dx. Things that go infinitesimally small, they always turn out to give you derivative values or differential values. So that's why this, summing up from I equals 1 to n, f of x sub I delta x. And the context was f of x represented the height, or f of xi, excuse me, represented the height of one of these rectangles at the x sub I value. Delta x represents the base. So you're summing up for all n rectangles, height times base for each one of them. And then you kind of animate your n to get infinitely large, so that way you get more and more rectangles, refining your estimate. And when this limit exists, this turns into the definite integral for the function f of x with the differential dx. So everything here has a counterpart. The sigma becomes the stretched out integral sign. The f of xi becomes your integrand, your f of x here. And then the delta x becomes the differential dx, all because delta x shrinks down to essentially a point, in the evaluation of this limit. Going one dimension higher, this is a function of one variable and it has the x-axis as its domain. So one dimension extension above that deals with double integrals, okay? And this is technically beginning chapter 15. One of the other major topics in Calculus 3, multivariable calculus. So a little bit of, behind what we're actually trying to measure. And it's kind of analogous, so I'm not going to go through the full Riemann thing. If you had to evaluate limits of Riemann sums in Calculus 2, we'll just let that be your experience with that and say there is an analogous experience here, but you're not going to have to worry about it, okay? So what you want to do is you want to I'm going to introduce it in the context of volume, okay? Definite integrals are introduced in the context of area underneath the function's graph above the x-axis. Well, now we're going one dimension higher with our functions. That we have a function of two variables. So it has a two-dimensional domain in the xy plane, okay? And it has a surface up here like this. So the assumption is, if you're dealing with volume, that the function's entirely positive. The outputs of this function, this sort of chunk of the function, is up above the xy plane. So all the z values of this function are up above the xy plane. And we take a snippet of its domain down here, some sort of rectangular region. I'm calling it R, generically. It's just some kind of underlying rectangle. It could be a square, just some region in the xy plane in the domain of the function underneath the surface itself. And to develop the way this works, we want to find the volume that uses this region R as the base and then fills in all the space from that base up to the graph of the function. And so we're kind of looking at a transparent version of the solid right here. But imagine, everything's solid from here up to the function. That's the chunk of volume in 3 space, the cubic capacity we're trying to find. And in order to do that, the Riemann logic behind it is you break this region down into smaller rectangles by dividing the sides into delta x and delta y partitions, okay? And just for convenience sake, we'll say each of these delta x's that run, in the x direction, they're all equal length, and the delta y's are also equally spaced, all right? They don't have to be, but again, it's just kind of convenient for the picture to see that. So, just like those Riemann rectangles in Calculus 2 give you approximations of the area from the x-axis to the function, when I take this region here in R, I pick some x, y value that's in each one of those rectangular squares, those little tiny squares, and I say, well, evaluate each of those little chosen values of the function, and it turns out to give you these sort of prisms that come from each of the squares in the base up to the function. And you can see it's still a rough approximation at best, because there's a lot of gappage between the top of each of these prisms that kind of run flat and the organic surface of the function itself. So it's still, at best, an estimate. But the estimate for the volume comes from, erase this. The estimate for the volume comes from, the volume of one of these rectangular solids would be the height times the base area, okay? Most often you think of rectangular solids as length times width times height, but if you've already got a two-dimensional base that's defined as a rectangle or a square, you really just need to multiply that base area times whatever the height is. And because the height is determined by the function's values, height times base area translates to f of xi, yj, or f of xy just generically, times the base of each of these rectangles. Each one of these rectangles in the bottom are delta xy and delta y long. So the product delta x times delta y is their base area. So this is just the translation of what height times base area would be for this particular scenario. Okay? And then, assuming I've got a finite number of prisms here, to estimate the total volume, I've got to use a double sum. Okay? I need to sort of, pick a y value and fix it. So let's say we're picking this first y row right here, and I want to sum it up for the volume of each of these prisms that I have 1, 2, 3, 4 from right there. So if I fix this row and I add up as x goes from 1 to 2 to 3 to 4, and then that adds up the first 4 rows in that first section. Then I go to this next row and I do the same thing. X goes from 1 to 2 to 3 to 4 and adds those next 4. So you have to sort of double index your sum because you're summing up each row for each column that you have in the y direction. And so that's why it's going to need a double iteration on your sigma to get that. So, and here's where I'm asking you to take a leap of faith. I'm asking you to sort of, take the limit as m and n both approach infinity. And I haven't really told you, but m and n represent the number of rectangles I have up here in the xy plane. I mean, clearly in the y direction it's 5, in the x direction it's 4, but I'm trying to keep it generic. So we're saying there's m rows and m columns, and we want those to go to infinity, so that way the bases of each of these rectangles shrink down. You get more and more rectangles to make skinnier and skinnier prisms, so that way there's not as much gappage between the top of your prisms and the surface itself. And when that limit exists, big leap of faith, but it's not Hogwarts math, I promise. This is real legal stuff. Whenever m and n go to infinity, that forces your delta x and delta y to go to 0. Any and every time delta x and delta y both go to 0 simultaneously, they become differential quantities. The first time you saw it, you may not tied into it too much, because calculus 1 is still sort of a blur to a handful of you. But when you first saw it, it was in the context of turning secant slopes into tangent slopes. Okay, you measure the secant slope right here, and you have a delta y rise over a delta x run. Okay, and they come from the same function. So the slope that we're looking for is the tangent slope, and it's roughly delta y over delta x. But what you did in calculus 1 is you forced delta x to shrink down. You took the limit as delta x would go to 0. Most of you may have used h. If you use the difference quotient that you learn in pre-calculus, it's usually the limit as h goes to 0, so that's why this may look a little foreign to some of you. But if you force delta x to go to 0, force this to shrink on down, you're going to turn this secant slope into eventually a tangent slope, like that. Okay? And notice, as delta x shrinks, delta y depends on it. So when you force delta x to go to 0, both of these technically become this indeterminate form. Okay? But see, you didn't know L'Hopital's rule at this point. But whenever those increments turn into infinitesimally small 0 values, they technically become the differentials you know from derivative notation. Because that's how a derivative came about, is you force your delta x to shrink to 0, delta y is also shrinking to 0 as well because you're approaching the same point. And then it turns into the differentials dy over dx that you know from just regular derivative notation. So that's probably the first time you shrunk something down to where it became 0 and then turned into a differential. Same idea here. Delta x and delta y are shrinking to 0 as we allow those two things to go to infinity. And in that process, your sigmas become double integral signs. Your function is still the integram, but now it's a function of 2 variables. And your differentials delta x, delta y become the differentials dx, dy. So it's just an extra iteration on your integration. That's all it is. You've got 2 variables in your domain. That means you need 2 variables for integration. And it may not be intuitive as to how to evaluate it at first, but I've got some problems I want to show you just to see how how it's actually done. So what this actually represents is if the function f of xy is all positive, like this one is, and you evaluate this double integral over whatever the region R is, you're actually calculating the total volume based on having that rectangle R as the base and the function is the height of this kind of rectangular solid out there in space. So Calc2 single integrals were area under a curve. Calc3 double integrals are introduced with that context, volume underneath the surface. Now later on in Calculus 2, you eventually deal with integration and you kind of tie away from that context of area under a curve, because you can get negative answers for an integral, you can get zero answers for an integral. So it's not always necessarily calculating area under a curve, and we're eventually going to extend this. This isn't always necessarily going to measure the volume underneath the surface. Okay. So far so good. Too soon to ask, probably. Let me show you. Page 2. So, but again, first, the healthiest context to introduce this in is the notion of finding volume underneath the surface. So, whenever you're evaluating a double integral, or sometimes you may hear them called iterated integrals, because we're also going to be doing triple integrals as well at some point. Here, the domain of the integral is a two-dimensional region in the xy plane. Later on in chapter 15, we talk about the domain of an integral being a 3D region in space. That I can't draw a picture for. I can draw a picture of the domain, but I can't draw a picture of the fourth dimensional range, you see? In this case, these functions have a two-dimensional domain in the xy plane, so we can talk about the function being the outputs, or the z-values, or the range of those inputs. So you can kind of see a picture, and you can tie it in with your existing notion of a 3D solid, from the base, filling in that space all the way up to the function itself. But if you go one dimension higher for a triple integral, it's kind of hard to picture that one, all right? But it's still analogous. It still works out the same way. So we're integrating over rectangular regions first. So I've got this set builder notation here that the region R is the set of all xy points in the xy plane from A to B for x and from C to D for y. So in other words, we'll just say generically, if that's my xy plane, x goes from A to B, so you have a couple of x values that designate that part of the domain, and you cross-reference that with y going from C to D. So if I have this as the set representing the domain of the double integral, it's really this rectangle in the xy plane. This is the region R that we're kind of generically talking about here. That represents the double integral's domain. You see? So at first, you're only integrating over rectangles, okay? And according to this, the double integral over the region R, you actually take these values here and plug them in on the integral's limits, just like you do a definite integral from Calculus 2. But notice, there's something you got to pay very, very, very careful attention to. Whenever you're integrating over a rectangular region, like I'm introducing to you here, notice the order of integration that you could have. You only got two, you got just a choice. You could do the dy dx order, or your differentials could be in dx dy order. So when you're integrating over rectangles, you can flip them. But notice, y's values have to go from C to D. So whatever differential is here has to have the corresponding y values on that inner part of the iteration, the inner part of the integral. And then the x differential is listed last. So that fixes the x values from A to B to be on the outer integral. So in other words, if your differentials are dx dy or dy dx, you have to match them kind of like bookends. The x values go with the dx and the y values go with the dy. So if I switch the order, it's no different. It'll give you the same value. But if dx is first, this inner integral has to have the x values A to B. And if dy is last, the outer integral has to have the y values C to D. Okay? So just make sure you have them sort of matched up like bookends, kind of going from the inside out. And that's actually the way you evaluate it. You just kind of go from the inside out. One thing you haven't done yet, though, is a partial antiderivative. That's exactly what you do whenever you do a double integral. Well, let me show you. I want us to set up, or just evaluate this double integral first. And then later on, I'll sketch the actual region of the volume this thing calculates. So just as an evaluation, that's the main thing I need to make sure you get. Just the evaluation, you just want to go from inside out. So when you set up this integral, it's already set up for you. The outer limits are 0 to 2. The inner limits are from 0 to 1. The integrand, the function, is 8 minus 2x minus y. And according to the problem, we're doing dx, dy order. So first off, what's the domain of this integral look like? If I were to sketch the domain region that we're integrating over, not sketching the surface, just sketching this domain.
On x, it's from 0 to 1.
0 to 1 for x,
Y
and
0 to 2.
0 to 2 for y. So it is a rectangular region that we're integrating over. This is the snippet of the xy plane that provides the domain of this integral, okay? So, in other words, this was also touted as a volume problem. Whenever your function is entirely positive, now, you may not be able to look at that and tell that this function is entirely positive, but if you think about the outputs, if my x values range from 0 to 1, this goes from 8 minus 0 to 8 minus 2, so that would still be positive. And then as y ranges from 0 to 2, it'd be 8 minus 0 minus 0, and at the worst, 8 minus 2 minus 2, 4. So you get entirely positive outputs for this function for all the xy inputs you can generate from that rectangle, okay? So this is an entirely positive function, which means we can talk about this being a proper volume. This thing provides the top of whatever the solid looks like, and then there's vertical walls that go down to the xy plane, and then there's that rectangle providing its base. So whatever this solid looks like when it hits the tabletop, that's the indentation it would make on the tabletop. That's the contact surface, okay? So now evaluating it. I've mentioned inside out, so sometimes you'll see double integrals with these nested parentheses around them like this, because that's really kind of the order of operations you have to commit to evaluate them. So if my first differential is dx, integrate first with respect to, and I abbreviate that just like Beth does, WRT. Integrate with respect to x first, treating y, any use of y, as a constant, just like you do with partial derivatives. So it's just the antiderivative counterpart to doing a partial derivatives. So when I do that, so what I actually do is I kind of just take the inner integral and sort of set it up by itself. The integral from 0 to 1 of 8 minus 2x minus y. My first differential is dx. So just treat it like if you need to, turn it into a calculus 2 problem with this addendum. Since dx is my differential, I'm focusing all my antiderivative rules and techniques on x. Any use of y is treated as a constant. And keep in mind the role of a constant in integration. Standalone constants, when you're integrating x, become what? Like if I integrate the constant 5, it becomes 5x. Okay. If you integrate the constant y, it becomes yx or xy, because I'm the same way I do alphabetical order. Yeah. So any use of y is treated just like any kind of constant. So this thing's antiderivative with respect to x should give me 8x minus x squared, power rule kicks in there, and then minus y is constant just like the 8 was. So that becomes minus xy. Does that seem pretty straightforward? Okay. Your limits are 0 to 1. Those values get plugged in for whom? X, because y is still held constant in this instance. So when I plug in 1 for all the x's, that gives me 8 minus 1 minus y. When I plug in 0 for all these x's, everything annihilates. So I'm left with 7 minus y from my inner, I'm going to tongue tie myself, from my inner iteration, the inner part of the integral. But we're halfway done.
2 to 0 with that.
Yeah, now you want to go back and integrate with respect to y. And now, since one of your iterations is gone, you've technically turned it into a regular calculus 2 integral. Because all that's left to do is apply the 0 to 2 limits for the function 7 minus y dy. So now you're going back and catching the outer iteration. So far, so good? And so, yeah, and that's just like a calculus 2 integral. Your antiderivative is 7y minus half y squared. Limits of 2 plug in first and 0 plug in last. So that gives me 14 less half of 4 is 2. 0 wipes everything out in that polynomial. So we get an answer of 12. Your first double integral gives you an answer of positive 12. And over here on the left, I want to fill in a picture of what that 12 stands for. Okay? And that's the way you should evaluate any double integral. Some big differences between calculus 2 and calculus 3 with these double integrals. You will never see an indefinite double integral. You see, in calculus 2, you had to do some integrals with limits that were definite integrals. You do your antiderivative, and in that case, you could forgive the plus c. Some of them were just for the purpose of integrating and finding an antiderivative, a general antiderivative, and then you would need the plus c if there were no limits on the integral. Those were called indefinites, and the one with the numbers were called definite. Every double integral you should ever encounter in this class should be a definite integral, or a definite double integral. Okay? The only time it wouldn't be is if we just need to do a partial antiderivative for maybe solving some kind of problem.
Solve for only x or something.
Or solve, like if those of you who've had differential equations, if you, early in the semester when you were solving exact equations, you had to integrate with respect to x and then alternately integrate with respect to y, or do sort of a partial derivative kind of thing. Same idea. We're gonna, eventually do that when we get, but we don't see that till chapter 15 when we start dealing with conservative vector fields. So that can go in one and out the other at this point. All right. But all the double integrals you should be evaluating are going to be definite double integrals. But I do want to show you a picture of what the heck this 12 stands for. Okay, because this is the function we're integrating. That's our f of x, y. So I want to sketch the graph of z equals 8 minus 2x minus y, my integrand, over this rectangular domain that we just integrated over, just to give you an idea of what this measures. So what I need to do is skew this for 3 dimensions. So down here's my xy plane. And here's my z axis. Okay, so this rectangle, if I superimpose it here, x goes from 0 to 1, and y goes from 0 to 2. And so it looks something like this when you kind of project it in a skewed diagram like this. Okay. So it's the same as this. I'm just laying it down flat on the tabletop. Okay. The easiest thing to do is first off recognize what kind of surface this is. Everything's linear. Nothing squared. Nothing divided by x. Nothing. No asymptotic behavior. No divided by 0. So if everything's linear, what kind of surface would that generate?
Rectangle.
3 dimensions.
Cube or something?
Rectangle.
Okay, you're thinking about the entire solid.
Yeah.
I'm just talking about just the surface up here on the top. See, this is the domain, and if we plug these values in, it should generate a plane. The top of this solid is just a plane. When you're dealing with a 3-variable equation and everything's linear, it's going to be a planar surface. Okay, a tilted plane, but it'll just be a tilted plane like that. And so the easiest points to plug in to see the top part of the surface is just maybe the 4 corner points. If I plug in the origin, x equals 0, y equals 0, I get a z value of 8. So the z-intercept for this plane should be up here. Let me set a scale. I'll say that's 8 right there. So that means that's about 4. Okay, roughly. If I plug this point in, that's an x value of 1, but a y value of 0, because you're only on the x-axis. And keep in mind, that's a function of 2 variables. You're plugging in x's and y's to get your outputs. So I plug in x equals 1, and then y equals 0. That gives me a z value of 6. 8 minus 2 times 1 minus 0. So this point would project up and give you a z value of 6. So it's roughly, you can say about there. This other y-intercept, if I plug this point in, and so this is understood to be directly above that point. Okay. When I plug this point in, that's an x value of 0 and a y value of 2. So that would be 8 minus 0 minus 2. That also gives you a z value of 6. So 6 is about there. Let me bring it over here kind of skewed. It's about that high up. Okay. So far our plane looks like this. If we're just looking at the snippet of the plane that lies above that rectangle. So it's kind of tilted. It's got a tilt to it. And then the other point to plug in is this one, where x equals 1 and y equals 2. If you plug them both in at the same time, 1 for x and 2 for y gives you 8 minus 2 gives you 4. So that should give you an output of z equals 4. So it's right about there, maybe. So this chunk of the plane that's up above our domain looks something like that, okay? Now, some of you already mentioned rectangular prism or rectangular solid or something like that. The actual volume that we're finding is the three-dimensional space that has this as the base and projects up to this function as its top, as its lid. So if I connect these laterals to make edges to the surface, you can kind of see the whole rectangular prism effect. And that's technically the solid we just found the volume for, okay? Now in this case, you could probably use just regular geometry to find the volume of a solid like this. Keep in mind, this was a z height of 4, right? So, to find the volume here, since everything up here is linear, you could probably average those z values to get the average height. The average height of this thing is, you know, the extreme 8, and then the other extreme, the lesser extreme, is 4, so their average is 6. So this thing kind of roughly, and heck, the endpoints right there are also at 6. So if you were to morph this to where it had the same volume, it has an average height of 6. And if this prism has an average height of 6 and a base area of 2, the volume should be base area 2 times average height 6, 12. And so you kind of check it that way, but here's the only drawback. That only works for planes. If you had like a paraboloid on the surface or something more curvy or more organic shaped, no love there. You have to just completely trust the evaluation you get from your double integral. Okay? So that's our f of xy. Finish labeling my picture here. Oops. And it comes from the equation of that plane. Here's our region R, the underlying region of the xy plane beneath, the base of the solid. And then that whole three-dimensional space from there up to the lid has a cubic capacity of 12. Even if it is a volume problem, you don't have to say cubic units after the 12. Just list the scalar 12 as your answer. And if the problem has the context of volume, I know that means cubic capacity. Okay? Make sense? Do you believe it? It's not April Fool's anymore. I'm giving you good stuff. Although, I had a really good April Fool's joke played on me yesterday. 8:35 a.m. Calculus 2 class. My best student, she's sitting in the front row. She's 8.5 months pregnant.
Oh, wow.
She's likely to deliver before the final exam, so we'll work that out later. But we're doing a partial fraction problem. Everybody's engaged. We're working like crazy. And then she looks at me, Mr. Crossland, I've got to go. I'm like, no. I just immediately start thinking, where can I get boiled water and towels? And then, you know, everybody in the class starts laughing, and they're all in on it. And then she lets out her April Fools, and I turn like 20 shades of red. But it was a pretty epic prank. Okay, so just, let me show you another example of a double integral over a rectangle. Now keep in mind, you know, the first context you're introduced with this is volume underneath the surface, okay? You're going to have double integrals that evaluate as negative numbers. You're going to have double integrals that evaluate as positive numbers, and some evaluate as 0. So it doesn't always have to be in the context of volume where the function is entirely up above that region of the xy plane. Here, we're integrating over, it's another rectangle. Your rectangle is in the y direction going from -1 to 1, and in the x direction goes from 0 to pi. And I keep drawing these rectangles just to give you a mental image of what we're doing. You don't have to do that as part of the problem, but the rectangle here, well, y goes from -1 to 1, so I need a little more y-axis down there.